In this video, let's switch back to a system level in a SerDes top-down picture instead of bottom-up narrow pictures images here. For example, we introduce a few equation images to approach a churn loss of 30 dB or beyond at a next rate. So, from the circuit images, there's no problem at all to equalize the 30 dB, 40 dB, or even the 50 dB loss on the next rate nowadays. Could you please tell me why we still need a low loss channel in a SerDes? Think about the PPA images for 5 seconds. Bingo! PPA is the performance in speed, power, and area. As you may notice, we need higher speed for greater amount of data transfer needs over the high-performance computing AI, cloud data center, automotive, 5G mobile, switches and routes, die-to-die, chiplet, etc. applications. But a higher speed leads to a higher churn loss. Therefore, we need to pause a bit and think about the pitfalls of the higher churn loss from the PPA images. Before that, let's define the power in another way, such that we could make sure of an apple-to-apple comparison. Yes, if you are familiar with the SerDes design, you should know energy efficiency pretty well, and bear with me. If not, let's go through this power and speed image together, and you will have a better feel why you need a figure of merit FOM in the energy efficiency. As you can see, SerDes A consumes 100 mW, while SerDes B consumes 20 mW. Which SerDes has a better power efficiency? SerDes B, right? No, you should ask me what the data rate of each SerDes operates. If I told you the SerDes A consumes 100 mW while operates at 20 gigabit per second, but the SerDes B consumes 20 mW while operates at 1 gigabit per second, then you realize the SerDes A is actually lower power than SerDes B in each bit. Therefore, we need to define the energy efficiency with the power divided by the data rate, which is 100 mW divided by 20 gigabit per second equals 5 picojoule per bit shown here. Similarly, if we can benchmark that the SerDes B has a poor power efficiency, since it has 20 picojoule per bit, much bigger than the SerDes A's 5 picojoule per bit. Then let's start to look at the pitfalls of energy efficiency. One of the wireline systems push the SerDes speed higher is Ethernet, owing to the higher demand in the data center driven by the cloud computing or AI. The speed requirement will reach 1.6 terabits Ethernet. Another interesting image of the data center room comparison is very messy in 2009, but must be clean and well organized nowadays, owing to the C-Link or SerDes. Therefore, reducing the number of wires over I/O is one motivation to push the line rate higher in each SerDes. The image of the line speed data rate trend in Ethernet may give you some idea. In 2009, the line rate was 10.3125 gigabit per second, then 25.78125 gigabit per second, around 25 over 28 gigabit per second in 2016, 56 gigabit per second in 2019, and 112 gigabit per second in 2021. Even though the 224 gigabit per second we have reported in this year I'm not sure if that's workable in production unless people have a better system design, which is the reason you may need to know what a raw loss in a SerDes is. Let's map what the loss is according to the line right here. As you can see, the worst case channel loss defined by the 10G Ethernet is 25 dB ball-to-ball loss at a 5.1625 GHz next rate of 10.3125 gigabit per second, and the total budget could still be 30 dB if we keep the same PCB material in loss per inch and backplane length. The loss would be greater than 50 dB easy, around 12.5 GHz, which would not be feasible for 25 gigabit per second for sure. Therefore, the 25G Ethernet still defines roughly 25 dB ball-to-ball loss at the next rate to enforce all the system design in the PCB and package design for 25 G link still can work properly, but we still hit the loss limit as we go beyond 56 gigabit per second, and the loss at the 28 GHz is still possible to be greater than 50 dB, since we cannot make a better loss material with low cost or even shorten the length of the backplane. So what can we do? Think about the painful images for 5 seconds. Bingo! In the Why Painful SerDes video, we will talk about how the 4-level painful 56 gigabit per second can have the same data bandwidth as the 2-level NRZ 28 gigabit per second up to the next rate of 14 GHz. Obviously, the insertion loss difference of 28 GHz and 14 GHz data IL is greater at least 25 dB. So even though the painful SNR will degrade 9.5 dB due to the 1/3 voltage swing over NRZ swing, the painful is still a better choice. This may explain why everyone goes to painful if the data rate is moved to 56 gigabit per second Ethernet from 32 gigabit per second PCIe 5. This is also part of the reason why we need a low loss in a SerDes. In addition to the design challenge and the high loss and high data rate, what else could be the issue? Correct. Power consumption and its corresponding energy efficiency. Let's assume we can magically keep the energy efficiency the same over different data rate. Also, we can assume the power scale with the data rate. Then that's 50 milliwatt in one lane 10 gigabit per second SerDes, but that will be 1.1 watt in a one lane 224 gigabit per second SerDes I/O, which will blow up the power a lot and create a big thermal issue on the chip, package, and backplane. Therefore, keeping the energy efficiency the same is not good enough, and we must even reduce the energy efficiency if we need to keep increasing the line rate. Unfortunately, according to our observation in the literature, the energy efficiency picojoule per bit increases as the churn loss increases, which implies to push the power higher if we don't limit the churn loss. Could you tell me why is that beyond this imagery? Right. Equalization EQ images should tell you the image of energy efficiency versus the churn loss. First, in an extra shortage over 3 to 5 dB loss, the IX can have a simple CTOE to equalize the loss easy without increasing the TX output swing and power, which could be only 1 picojoule per bit or less. Second, as the loss moves to a very short reach over 6 dB to 15 dB loss, not only the TX output swing needs to increase, but also the TX FV needs to edit maintain a robust operation for the CTOE over PVT and higher input sensitivity. Therefore, the energy efficiency may go up to 2 to 3 picojoule per bit. Third, between the short reach or the medium reach, the loss will go beyond 25 dB, and we may need the DFE to increase the input sensitivity without adding too much noise amplification from the TXFV or RX CTOE. So the energy efficiency must need at least 4 to 5 picojoule per bit. Fourth, in the long reach or loss greater than 30 dB, the whole SerDes, including the TXFV, RX CTOE, RX DFE, may be sensitive to any intrinsic impairments. Therefore, lots of complicated calibration and correction in the analog blocks will increase the power efficiency up to 6 picojoule per bit. Finally, if the channel loss approach to the very long reach up to 45 dB or higher, what should we do? Correct. Back to the PAM4, and the extra DSP may be needed for the ADC-based RX such that the energy efficiency may go up to 7 picojoule per bit. Hopefully, these EQ images provide an intuitive way of why a higher loss will increase the energy or power greatly along with a lot more complicated circuit blocks here. Here are the summarized images of why we need a low loss in a SerDes. Even though we discussed lots of circuit images can help us to equalize the 30 dB, 40 dB, or even possibly 50 dB loss at the next rate nowadays. But we may need to revisit the SerDes topology from the top-down system level instead of a bottom-up circuit design. Therefore, the PPA of a SerDes is very important, such as the high-speed requirement or trend in the Ethernet. If we keep increasing the speed from generation to generation without changing anything, we may face a channel loss of more than 50 dB, which is not even feasible in circuit design. Therefore, from 10 gigabit per second to 25 gigabit per second, we keep limiting the channel loss by reducing the channel length and improving the material. But we must change signaling from NRZ to PAM4 for data rate greater than 50 gigabit per second, since we couldn't make any better in the holding budget. So the PAM4 SerDes kind of tell you why we need a low loss in a SerDes. But the most critical motivation of a low loss requirement is the power image from the power versus the SerDes line rate, assuming the same energy efficiency. The one SerDes I/O only burns 50 milliwatt at 10 gigabit per second, but the power ends up to 1.1 watt at 200 gigabit per second. Unfortunately, the energy efficiency should be much worse in the 200 gigabit per second PAM4 SerDes if the channel loss is the same or even higher. Since at such high data rate, the SerDes must need the TXFV with a high swing, RX CTOE, RX DFE, lots of digital power in DSP, and all the calibration correction blocks to add much more power due to the high capacity. Then the power at 200 gigabit per second SerDes will blow up the chip over big thermal issues anywhere in your system if we don't limit the channel loss to a reasonable low enough level. Thank you for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share comments down below. Lastly, please share the video link with the people who may be benefiting from it.